So in this question, we have two charged spheres, and these two charged spheres are kept at a finite distance, as shown in the figure, like they have a centered center spacing. Your force of electrostatic interaction between them is first calculated. Assume them to behave like point charges, like they are. You can assume that they are behaving like point charges, where the entire charge is concentrated at the center, and then you're measuring the force experimentally, right? So the force which you're calculating, assuming that they are placed at the center, is given by Fc, and the force you're calculating and the force you're measuring experimentally, that is given as Fm, right? So if you notice, in all of these options is given, he's asking you a relation between what will Fc and Fm be if these charges were unlike charges or like charges, and what kind of material should the sphere be made up of, right? So a very conceptual question. So let's start dealing with this. So let's assume that we have like charges at the beginning. So I have this sphere, I have this other sphere, and let's say they are both positively charged. Let's say they're both positively charged. Okay, so this is a general idea which we also use in Coulomb's law as well. We can assume spheres to behave like point charges at the center, but there are terms and conditions, or there are actually restrictions on how we can use it, or rather, I would say it's an approximation actually, because there are things which change over here, and that is what this question is trying to point out in this case. So if I have like charges right now, which is what I have in this case, these like charges would also exert a repulsive force on each other, is something we're aware of. So because of this, the charge distribution on the sphere changes. The charge distribution on both the spheres will be kind of this way right now. You'll have charge concentrated more on the left side of this sphere. You'll have charge being concentrated more on the left side. You have charge being concentrated more on the right side in this case, right? So is this assumption valid then? I mean, if we now try to actually calculate what would be the force acting between them, then I can no longer assume that they're actually, this charge can be placed at the center. This can only be done if your charge is uniformly distributed over a sphere. And now, because the distribution of charges shifts towards the left for this left sphere and shifts towards the right for this right sphere, we can assume that the entire charge is concentrated slightly towards the left of the center of this left sphere and slightly towards the right of this center of this right sphere, right? So what was your calculated value when you're calculating the value of force acting between them? The force expression which we are writing, that will be equal to, so that force be equal to Fc. So that will be equal to K Q1 Q2 by R1 squared, right? But what will be a measured value of force? A measured value of force in this case will be equal to K Q1 Q2 by, it's an approximate expression. These are not point charges, so we are approximating it. But a measured force approximately will be equal to K Q1 Q2 by R2 squared, where R2 is now the distance between where I can assume the entire charge is concentrated. And as you can see, R2 is greater than R1. So your measured value of force here will turn out to be less than the calculated value of force, right? And this distribution of charges will happen irrespective of what material I'll have over here. So if it's a conducting sphere, your charges will distribute, more freely, as in the charges can move more freely, and this distribution will happen to a larger extent. Whereas even if this is an insulator, also induction will happen in inductor as well, right? So this result is true irrespective of the material of the sphere. So if your spheres are made up of like charges, then we'll see that the force which we are calculating using the formula, that is the charge is concentrated at the center, will be actually greater than the force value which is being measured experimentally, right? Similarly, now I think you should be able to arrive at an idea for how the expression will be when we have unlike charges. So when we have unlike charges, so let's say I have a negative charge on this sphere and I have a positive charge on this sphere. So when we have unlike charges, we know that these charges attract. So what happens in this case is your negative charges will shift, more closely to the positive sphere, and your positive charge will shift more closely towards your negative sphere. Right. So once again, our calculated value of force, the force value which we're calculating, assuming that the charge is entirely located at the center, will once again be similar to K Q1 Q2 by R squared, where Q1 is the charge given to this and Q2 is the charge given to this. Right. But now, because your charges are shifting more towards the right for the left sphere and more towards the left for this right sphere, we can now say that if I have to assume a point where the entire charge is concentrated, where we can use the word center of charge as well, I'll now say that the entire charge is more closely, I can assume that this entire charge is now concentrated to the right of the center right now. So I can assume that this Q1 is located over here, and that's a negative Q1 in this case. And I can assume that this Q2 is located more towards the left of the center. That is in this case here. Right, so let me write this force expression as R3. Let me assume that this distance is r3 right now. So what would be a measured force value in this case? A measured force value in this case is equal to k q1 q2 by r3 squared approximately, right? And from the diagram itself, we can see that in comparison to the actual value. So if you assume that they were located at the center, if I assume that this entire charge is concentrated at the center, then that distance would be equal to r1, let's say. Then your measured force value, your calculated force value, your calculated force value in that case will be equal to kq1 q2 by r1 squared. But the measured force value will turn out to be more approximately to kq1 q2 by r3 squared. And we can see that r3 is less than r1. So in this case, your measured value of force will be greater than your calculated value of force. So this was an interesting concept, highlighting when these formulas are actually applicable and when we actually perform an experiment, how would these values actually change, right? So hopefully the answer for this question is clear. So irrespective of the materials, irrespective of what materials we have over here, because induction or the charge distribution can change, whether you have a conductor and insulator, your calculated value will be greater than the measured value for light charges, and your calculated value will be less than your measured value for unlike charges. So option D is the most relevant in this case. Right, so hopefully this question proved useful. I'll see you guys again in the next question.